Hi, this is chapter 4, the section on balancing chemical reactions. So in this particular discussion, I'll show you how you go about in looking at a reaction and making sure that it makes chemical sense in terms of making sure that it obeys the laws of law of mass of conservation of mass. Whenever you have a reaction or you're making a product through a synthesis, generally what happens is that you have to make sure that the material that you have in the beginning also shows up at the end. And I'm not talking about the chemicals, I'm talking about the atoms that make up the chemicals. So here are a few examples of some chemical synthesis. And the first one right here is a nylon synthesis. In this particular case, you have a monomeric unit right here. And the monomeric unit shows that this particular chemical binds with this particular chemical and repeats itself. This binds to the left of this chemical through the nitrogen atom, and then this also binds to this chemical through the nitrogen atom, and it keeps repeating where these are what we call the monomeric unit, and then it forms a very long chain called a polymer. And that's how nylons that you see in parachute as well as stockings is synthesized. And this right here is the reaction or the synthesis of aspirin. We start with salicylic acid. That's this chemical right here. It's an acid because it's got this COOH group. So that's salicylic acid. This right here is acetic anhydride. That's this chemical right here. And what happens is that it's a straight addition. It's a straight reaction in which this group right here bonds to this oxygen over here. So you have that right there. And then this group right here picks up the hydrogen, and you have this right here. This chemical right here is acetic acid, the same acid that you find in vinegar. But the important product is this chemical right here, acetyl salicylic acid. It's this acetyl group right here that causes the magical properties of aspirin. This third reaction is the reaction by which Mother Nature takes carbon dioxide, that's the gas that we breathe out, with water in the presence of light to give this chemical right here, which is glucose, which is nothing more than a sugar. And you notice it's not balanced right now. We're going to be talking about that because right now, as you see it, there's only one carbon atom in carbon dioxide, and yet there's 6 carbon atoms in glucose. There's 3 oxygen atoms from carbon dioxide and water, and you have 6 here. So what we need to do is go about in balancing this reaction so that it makes chemical sense, and that's what this chapter is about. So first thing that you need to know is what are the symbols and what information do you get from a chemical reaction. The first is that the law of conservation of mass is obeyed. That is, the chemicals on the left, or the atoms on the left, also shows up after the reaction. The arrow here tells you that this side is before the reaction, and this side is before the reaction, and this side is after the reaction. So you can think of this equal sign in terms of an arrow sign, in terms of an equal sign. So let's take a look at this. What we have is, in this particular reaction, I'm taking hydrogen molecules, and there are 12 of this. That means that we have 12 of this type of compounds, 12 of this, and I won't draw all 12, but you get the idea that this represents 2, and you need 12 of these. in combination with 6 of these, and molecular nitrogen has a triple bond in between them. You don't really have to know about the structure at this point. Just know that N2 represents this chemical, and we have 6 of these. So you can see right away, based on this information, you've got 24 hydrogens in the left side, 12 times 2, and you've got 12 nitrogens atom on the left side. And what we're going to do is, when the reaction proceeds, you see that for every 1 nitrogen, 3 hydrogen is consumed. That's what an NH3 is. For every 1 nitrogen, you have 3 hydrogens hooking up. See, there's a chemical reaction that takes place right here. And we have 8 of these. And if you take a look at this right here, 8 ammonia means that there are 8 nitrogen atoms in the 8 ammonia, and there's 8 times 3, 24 hydrogen atoms in the 8 ammonia. Now if you take a look at the left, you see that the 24 hydrogens and 24 hydrogens agree with each other. So we can say that the hydrogens are conserved. But here you have 12 and here you have 8. That means 4 of these didn't convert to ammonia. That means that you still have 4 nitrogen left over. It means that 4 nitrogen means that there are 2 ammonia unreacted. So that's how we go about in balancing this reaction, is that we notice that we look at the atoms and what these numbers mean. These are called the coefficients, and we start going back and forth so that we account for each of the atoms before the reaction and each of the atoms after the reaction, and these two have to agree with each other. Here's another example in which we have C3H8, and that chemical is called propane. And in propane we have 1. We don't show it here, but whenever you don't see a number in front of a chemical, it means there's 1 of this particular substance there that you're using. Now, this is already a balanced equation that I have. But what this C3H8 means is that there are 3 carbons, 1, 2, 3, and there are 8 hydrogens, 1, 2, 3, 4, 5, 6, 7, 8. And it combines with 5 oxygen molecules. There's 1, 2, 3, 4, 5, for a total of 10 oxygen atoms to produce 3 carbon dioxide, 1, 2, 3, and in the 3 carbon dioxide you have 3 carbons and 2, 4, 6 oxygens, and 4 waters, 1, 2, 3, 4. Now if we take a look at the atoms, we can see that the carbons are conserved. That is, there's 3 here and there's 3 here. You see that the 8 hydrogens right here is also conserved through these guys right here. There's 4 there and there's 4 here. And finally we have our 10 oxygens. There's 2, 4, 6, 7, 8, 9, 10. So this is a balanced reaction. There are no atoms that are going to be in excess or shortage. Here's another example. In this particular example, again, we're forming ammonia, but I want to show you again how these things combine. You have 9 hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9. And 6 nitrogens, 1, 2, 3, 4, 5, 6. And I'm showing you again the group that's going to form the product ammonia, and there's going to be 6 ammonia. There's going to be 2 here, there's going to be 2 here, and there's going to be 2 here. Remember, there's N2 here and H2 here, but there are 2 nitrogens and in this particular case 6 hydrogens. So that will yield for each one of these circled groups 2 ammonia. So that's what we see right there. And of course what happens is we get 3 high nitrogen that undergoes no reaction. I just again want to show you that these things have to combine in whole atoms, and that any unreacted also shows up in the product right here, but the net reaction is this right here. These are the atoms that cause a chemical reaction. Now the plus in a reaction means addition. What are the co-reactants? What are the co-products? That's what the plus is. The arrow means the reaction before and after. This symbolizes the before event and the after event. You can say that nitrogen and hydrogen forms or reacts to forms or yields 6-ammonia. That's what the arrow means. The S here tells you that the chemical that you have, now we don't have any S here, but the chemical that you're using in the reaction is a solid. The L tells you that the chemical you have in the reaction or producing in the reaction is a liquid. The gas, the G here, means a gas, and you can see in our example they're all in the gas phase. And AQ means that the chemical that you have in the reaction is dissolved in water. That is, it's swimming in water. So that's what AQ means. These tells you the condition by which the reaction exists in the chemical reaction. The arrow here with a diamond on top tells you that in order for this reaction to proceed, heat must be added. Some sort of metal like platinum or iron or some other element on top of the arrow tells you that this reaction requires a catalyst. Sometimes you'll see an arrow with this symbol right here, and if you remember from the previous chapter, this is the symbol for light, H-nu. So you can say that this reaction requires light for the reaction to proceed. So those are just information that you would use to get information, to get an idea of the conditions for the reaction. Now, what are the evidence? If you mix 2 chemicals, what are the signs that a reaction actually proceeded? I mean, you can't see atoms with your naked eye, but you can see the results of a chemical reaction, or detect or have some sort of instrument that can detect the signs of a chemical reaction. So what are the clues that a chemical reaction has occurred? Well, the first clue is that if you mix 2 chemicals, for example, and you see a fire or you see a spark, then that probably is a sign of a chemical reaction. An example is if you take ethanol or gasoline and you throw a match on it, it pretty much ignites. So that product at the end, carbon dioxide and water, is different from the starting material. So a chemical reaction proceeds. Remember that a chemical reaction proceeds when the chemical identity has been altered. The beginning material is different from the ending material in terms of chemical structure. What is another sign that a chemical reaction proceeds? You see a solid or precipitate. A solid formation when you mix, say for example, 2 liquids is called a precipitate. You think of precipitation when it rains because the gas forms a liquid. Well, in chemistry, when a solid forms from, say, aqueous solutions combining, that's a precipitate. Whenever you mix 2, say, aqueous solution and you start to see a cloudy tinge on the reaction mixture, that generally is a sign that precipitate has formed. Another sign that a chemical reaction occurred that is very difficult to detect unless you might have a thermometer or some sort of temperature gauge is a temperature change. When you mix 2 chemicals, for example, like sodium hydroxide in water, and the sodium hydroxide starts to go in, what happens is that the reaction gets very, very hot. But you can't detect that by sight. You have to use like your sense of touch or a thermometer. So a temperature change generally will always accompany a reaction, because when bonds break and bonds form, that involves energy, and whenever energy is involved in terms of bond breaking and bond forming, that changes the temperature Either it goes up or goes down. The last sign that a chemical reaction has occurred is a color change. But don't get confused of color change because you say mix red and green and get orange. Okay, that's just a mixture of two pigments. What we mean is by a reaction that takes place and the product that forms has a different color than the starting material. So that is a sign that a reaction has occurred. So whenever you write a reaction, the general form, the generic form looks like this. There are coefficients in front of the chemicals. Okay, coefficients in front of the chemicals. The coefficients tells you how many, but the chemical formula here identifies what substance are involved. The most important thing when you balance a chemical reaction or when you start is you have to make sure that you get the correct chemical formula. You get the correct formula written down. Otherwise, no use balancing it because your reaction, the reaction is not correct. So before you even start, pay attention to the chemical formula. Make sure it is the correct formula for the reaction that you're solving. Then proceed with the steps. So, in terms of how to proceed with the reaction, remember A, B, C, and D in this form right here represents a compound, represents a substance. The small a, b, c are the coefficient, and they tell you how many. So, going back to our example, this right here is propane. Propane, the formula for propane is C3H8. It combines with 5 oxygens. These are the chemical formula. The chemical formula for oxygen is O2. The chemical formula for propane is C3H8. You have to get these formulas correct because if they're not correct, you're starting on the wrong direction. No use start proceeding because it's already wrong. And it's forming carbon dioxide, 3 carbon dioxide, and remember that the formula for carbon dioxide is CO2, and 4 waters. And remember that the chemical formula for water is H2O. So when you start a reaction, make sure you have the correct formula. Then it's just a matter of going back and forth and making sure that the number of carbon atoms are identical, or the number of carbon atoms are the same in both sides. The number of hydrogen atoms are the same in both sides. The number of oxygen atoms are the same in both sides. And you make sure they're the same by changing the coefficient, how many each of these chemicals have. So that's the balance equation as we discussed last time. These are the coefficients right here. Even though you don't see a number there, it means it's 1. Here we have 5, here we have 3, here we have 4. So going back to this right here, the small d is the 4 in this example. The D would be H2O. The small c would be 3. The capital C would be CO2. The small b would be 5. That would be the coefficient. The capital B would be O2. That's the chemical formula. And here, the small a would be 1. And the big A would be C3H8. So that's what we have. We have C3H8, oxygen, carbon dioxide, water, and then we proceed with the coefficient. So let's start from let me show you another example. We have magnesium and oxygen from air. Whenever you see this word oxygen from air, or you just see oxygen in a reaction, know that the way oxygen is available for a reaction is O2. So don't put O the atom, but put O2 the molecule as found in nature, and then the product. So how would you go about in predicting what the product happens to be in this reaction? Now, you know that the symbol for magnesium is Mg. You know that the symbol for oxygen, molecular oxygen, is O2. And a lot of you will just go ahead and say, oh, Mg and O2, the reaction should be MgO2, because that's the chemical you have and you are obeying the law of conservation of mass. But remember what I said, you got to make sure that the chemical formula that you have in your reaction is correct. And this right here is not correct, because you know that magnesium, based on the periodic table, is +2, and oxygen, based on the periodic table, remember there's 2 oxygen here, so you have MgO, so that's MgO2. Each oxygen is -2. The fact that you have 2 oxygen tells you that the net charge of this chemical is -2. +2 and -4 is -2. That's not correct, because this is not electrically neutral. So you have to write the formula that makes sense, and the right formula for magnesium and oxygen is MgO. So that's what you have to write down when you start the reaction. Magnesium plus oxygen goes to MgO. And then it's just a matter of going back and forth and balancing this reaction. So if we go back and forth and balance this reaction, what you don't want to do again is write a formula that doesn't make sense. What you need to do is realize MgO is the correct reaction. You realize that there are 2 oxygens in the side, 1 magnesium, in this particular case, what you have, let's go back to this reaction right here. We have MgO, that's the correct formula, but you can see that you have 2 oxygen here and only 1 here. So what I need to do is I need to put a 2 right there. Now my oxygen is balanced, but you notice that I messed up my magnesium. Now I have 2 magnesium, I only have 1 magnesium here, so to balance that out, I would put a 2 here, and that's basically what we have down here, and that right there would be the balance equation. You don't change the formula, you change the coefficient in front of the formula to change the numbers, and that's the balancing process. So what are the different types of reactions that you will encounter? Well, if you just pay attention to the chemicals, you can see that SO3 and H2O, these are before the reaction because it's to the left of the arrow. SO3 and H2O combines and give 1. That's why this is called a combination reaction or an addition reaction, because you add these 2 to form 1. Phosphorus and sulfur combine to give you 1 chemical. Again, combination or addition reaction. Nitrogen and hydrogen produces ammonia. So that's the pattern that a combination reaction has. Let's take a look at the next one. This is a decomposition, opposite of combination reaction. Here you have 1 forming many. It could be 2, it could be 3, or it could be more. But you've got 1 breaking apart. So that's what we call a combination reaction. Okay? Of course, these reactions are not balanced. You can go ahead and practice balancing these reactions, but right now we just want to identify the different types of reactions. When 1 forms many, then that's a decomposition. When many forms 1, that's a combination reaction. So let's take a look at the next one. This is what we call a single displacement reaction. Reason why it's a single displacement reaction is because you got 1 element here, here and here, and you notice that the zinc replaces the copper, and you get zinc nitrate, and the copper gets bumped out. So that's why it's called single displacement, because 1 element displaces another element in a compound. It's an ionic compound. Here is another example. You might not see the single displacement reaction when I have it written as H2O, but if you write H2O water as this right here, you can see exactly what's going on. You see that the calcium displaces the hydrogen gets bumped off. Now you know that the calcium is +2, look it up in the periodic table. OH is -1, so you can't just write CaOH, because again, that Does not make sense chemically. This would have a net charge of +1. Calcium is +2, hydroxide's -1. That would be a +1 net charge. You actually need 2 hydroxide to get a formula that makes that is electrically neutral. That would be CaOH. So once you've identified the chemical in this reaction, calcium, water, calcium hydroxide, and remember, hydrogen doesn't exist as H plus when it is involved in a reaction. It'll form H2, the gas chemical. So that would be the formula, not H plus but H2. Then it's just a matter of going back and balancing this equation. But this is what we call a single displacement reaction, because the calcium here displaces that hydrogen and takes over in the formula. That's called a single displacement. This is what we call a double displacement, because again, what you see here is that the barium and the hydrogen in HS switches. The hydrogen will go over here and bind with the nitrate, and the barium will bind with the sulfur. That's what you get. Got to make sure that your chemical formula is correct. You don't want to write this as BAHS, because BAHS would not make sense. Barium is +2, HS would be -1. That's not correct. Two hydrogens has to be bumped off so that it can combine with the sulfur that's -2. This reaction, of course, is not balanced. It's up to you to balance the reaction. Here, this is a more classic double displacement reaction. The magnesium and the sodium switches partner. You have magnesium phosphate and you've got sodium chloride, sodium and chloride. It's a double displacement. Another form of double displacement is acid-base chemistry. In acid-base chemistry, the H and the OH forms water. The Ba and the anion in the acid forms this salt, this ionic compound. Write the chemical formula correctly first, then worry about balancing the equation later. Here again, this is the acid, this is the base. The OH and the H forms water. The NH4 and the Cl forms ammonium chloride. Double displacement. The last reaction is a combination. Combustion. Combustion is a reaction in which you have some fuel. In this particular case, we call it a hydrocarbon. Why is it called a hydrocarbon? Because it's got hydrogen and carbon in it. So any organic chemicals that has hydrogen and carbon in it are called hydrocarbon. And in a combustion reaction, 3 things you're looking for. In a combustion reaction, oxygen is always required for this reaction to start. It's a reactant. It's to the left of the arrow. So the oxygen is going to combine with the hydrocarbon. In this particular case, it's butane, and you form carbon dioxide and water. In a combustion reaction that deals with hydrocarbon, you require oxygen. You always form carbon dioxide and water, and of course, there's a big old flame, so you produce a lot of energy. Here's another combustion reaction. This happens to be glucose. This is how respiration works in your body. This is how you burn fuel or blood sugar in your body. You got glucose, you breathe in oxygen, you breathe out oxygen, and sweat water. So glucose and oxygen here, that's a combustion reaction, produces carbon dioxide, water, and of course the energy that you need to move your muscles. That's a combustion reaction. So let's take a look at some balancing guide. Whenever you have a reaction, again, this would be H2 here, and O2 here. Remember, do not fall in that pitfall that just because you see 2 hydrogens and 2 oxygens that you're going to change the formula and say that, oh, my product therefore has to be H2O2. You just violated you just changed the rule of the game, because the reaction is forming water, not hydrogen peroxide. So don't write hydrogen peroxide because that's not the chemical in the reaction. It's water, H2O. So just because it looks balanced, that doesn't mean it's correct because the chemical reaction is not chemically sound. So how do we proceed? We go ahead and realize that, okay, if I put 2 in front of that, that takes care of my oxygen. I now have 2 oxygens. Okay, but of course my hydrogen's messed up because I have 4 hydrogens and I only have 2 here. So the way you remedy that is, of course, you put a 2 right there. And if you do that, you see that the reaction is going to be balanced. 4 hydrogens in this side, 2 oxygens on this side. There's an arrow right here, remember? The two waters gives you 4 hydrogens right here and 2 oxygens right here. So that would be chemically sound, and it makes sense in terms of the reaction formula for the chemicals involved. So that's your net reaction. I cannot emphasize that before proceeding in balancing any reaction, you make sure that the chemical formula is correct. Now, seeing that example, let me give you a few hints as far as balancing chemical reaction is concerned. Here are just some hints. When you get the correct chemical formula, box the chemical so you do not change the formula. Remember, you change the formula by altering the coefficient in the for the chemical. You can change the coefficient in front, but never alter the subscript, I mean, of the chemical. Like this is H2O, this is H2O too. Just because you put a 2 in front of H2O, that's still H2O. When you start a reaction and you have your chemical identified and you believe that your chemical formulas are correct, then usually starting is always one of the more difficult aspect of balancing an equation. I always like to recommend that you start with the most complicated chemical and you give that a coefficient of 1. If you have to change that later down the line, then you need to do so, but that's a good start. Find the most complicated chemical and start balancing the atoms, the elements in that complicated chemical, and start by giving that a coefficient of 1. Save the chemicals that only have one type of atoms, like H2N2O2, as your very last step. And the reason why you want to do that is by altering the coefficients of these chemicals, you only alter the numbers of atoms for that particular chemical. Use fractions to balance odd number of atoms in the equation. I'll show you an example of that. And balance polyatomic cations and anions by keeping the polyatomic ions intact and balancing it as a unit. This really should go up here. When you do use fractions to balance odd number of atoms, convert your fractions to whole numbers, because there's no such thing as half an oxygen. You either have 1, 20, 30, but not 1/2 or 1.5. So these are just hints to go about when you balance chemical reactions. So let's do some examples. Well, here's a summary of what we just talked about. Box the chemicals so you don't change the formula. Assign a coefficient of 1 to the most complicated and start there. Balance elements with only one type of atom last. Use fractions to balance odd number of atoms. Convert the fractions to integer so that you don't have fractions in your balance equation. And then balance polyatomic unit as a whole. So here are 5 examples, and we will work with these 5 examples, and I will show you how I use these rules in these 5 examples. So the first one I give you is a reaction which I don't even give you the formula, I give you the name. You have to use the previous action to come up with the formula. Sodium oxide, that's NaNO. What is the chemical formula when you have Na, which is positive 1, and O, which is negative 2? Crisscross, remember? water, you all know the chemical formula. And then forms is an arrow. That's what that word means. Sodium oxide, water, arrow, sodium hydroxide. Sodium hydroxide is Na. Hydroxide, that ion is OH. So what exactly is the chemical formula for these? Looks like that. That's sodium oxide. Why there are two sodium there? Because each oxygen is -2, so you need 2 sodiums. That right there is water, H2O, and that right there is sodium hydroxide. So let's proceed by balancing, and the way I like to start is I just draw an arrow right up down the, I draw a line, right across the arrow, because this is before and this is after. And I want to make sure that my atoms before and after are identical in terms of numbers. So if you take a look at this, I'm going to look at sodium right here, and I'm going to see that I'll probably start with this as my 1, and right away you notice that I messed up. There's 2 sodiums here, you can't have 1 there. I'm going to change that to 2. Okay, I'm going to change that to 2. So that means that there are 2 sodiums in this side, and now there are 2 sodiums in this side by putting a 2 in front of that. So my sodium's okay. Let's take a look at hydrogens. Hydrogens, I have 2 here. I've got 2 here as well. So my hydrogens are okay. 2 hydrogens. Let me put a colon here. And 2 hydrogens here. And then finally let's take a look at my oxygens. My oxygens, there's 1, 2 here, and voila, there's 2 here as well. So this was a fairly easy reaction. All I needed to do was put a 2 in front of that sodium hydroxide, and it balances out. So this is what I would write down. 1, 1, 1. That would be the reaction that I have. 1, 1, 2. And what I usually ask in an exam or a quiz is, after you balance the reaction, what is the sum of the coefficient? So the sum of the coefficient is 1 plus 1 plus 2, or 4. So my correct answer here is, if I had a multiple choice exam and I say balance this and tell me what the sum of the coefficient is, I would select B. 4 is the sum of the coefficient. 1 plus 1 plus 2 is 4. Let's take a look at the next problem. Again, this is a word problem. Ferric, remember that this is the old system, but it is iron, and it's iron, Fe, not Ir, and that's +3. But you know that sulfur is -2. So you do the crisscross, and the correct formula for this right here would be Fe2S3. That would be the formula for that. Molecular oxygen is O2, and you guys can take a look and figure out what the formula is for ferric 3 oxide. It's probably the same as that. It's Fe2O3. Remember that oxygen and sulfur are in the same family. And then sulfur dioxide, SO2. So now that you have the correct formula, this right here, you can go about and balance this equation. So that's what we have. Now, again, take a look at before and after. We have 2 irons here, 2 irons here. So our iron is okay. 2 irons. 2 irons. Let's take a look at sulfur next. Remember, why am I proceeding with sulfur and not oxygen? Because this right here is the rule that I told you in the previous slide. You want to save that chemical for last, because by changing the coefficient in front of this chemical, oxygen, you only affect oxygen and nothing else. If you save the sulfur for last, by changing the coefficient here, which is where sulfur is found, you not only change the number of sulfur, you also change the number of oxygen. So save that as the last step. I'm going to balance sulfur next. And if you take a look, there are 3 here, and there are 1 here. Okay, when you don't see a number there, you can assume it's 1. So here it would be 3, here it would be 1, but we can make that 3 by putting a 3 right there. Now that's balance in terms of sulfur. Now we can proceed and balance oxygen. And oxygen becomes fairly simple just because of this right here. You save that for last. You don't put a coefficient in front of that. If you take a look, there's 3 here and 6 here. That's a total of 9 oxygens. But how do you get 9 oxygens when you have O2? If you put 4 here, that would be 8. If you put 5 here, that would be 10. Okay? So what do? Well, what you do is you put the fraction that I told you about, the fraction trick. So the fraction is, take a look at the atom. How many atoms you need? You need 9. Right here, you need 9. So I would use 9. And what is in the denominator? You've got 2 here, so it's 9 halves. 9 halves times 2 is 9. That would give you 9 oxygen. 9 halves times 2 is 9. So now your reaction is balanced. But of course this is a fraction, and you can't have a fraction in your balance equation. So the way to fix this is to go back and multiply everything in this equation by the denominator of that fraction. You multiply everything by 2. And by multiplying everything by 2, this now becomes 2, Fe2S3. This now becomes 9. This becomes 2. And this becomes 6. Remember, all the chemicals in the reaction needs to be multiplied by 2. And when you do that, this is the result that you get. The reaction would be this right here. You'd get, this would be, of course, 2. This would be 9. This would be 2. And this would be 6. So the sum of the coefficient would be 9 and 2 is 11, plus 2 is 13, plus 6 is 19. That would be the correct answer right there. The correct answer would be 19. Now let's take a look at this reaction. This is a reaction that shows the combustion of pentane. In the combustion of pentane, which is a hydrocarbon, what we have is C5H12 plus oxygen. Remember, combustion reaction requires oxygen to give water, carbon dioxide, and energy. So we proceed with this reaction. Again, let me just show you. And these might be the multiple choice question. When you have the combustion of pentane and you balance this chemical reaction, what is the sum of the coefficient? What you can see is I'm going to start with my carbon first, and you can see that I have 5 carbons here. So to make 5 carbons here, I would put a 5 right there. So that would also be 5 carbons. I would proceed next with the hydrogen and not the oxygen, because I want to save the oxygen for last. So I have 12 here. So for the hydrogen, I already have 12 here. To have 12 on the other side, I would put 6 right there. Finally, the last step is the oxygen. If you take a look at this, this is 6 oxygens and this is 10. Remember that for each carbon dioxide there are 2 oxygens, so 2 times 5 is 10. So that's a total of 16 oxygens. How do we get 16 oxygens in the other side? Simple enough to put 8 right there. So that right there would be a balance equation. You would have 16 oxygens here, 16 oxygens here, 12 hydrogens here, 12 hydrogens here, 5 carbons here, 5 carbons here. So when you look at the coefficient, there's a 1 right there. The sum of the coefficient would be 8 plus 1, that's 9, plus 11, that happens to be 20. So my answer for this question would be, what is the sum of the coefficient? It would be 20 right there. And in fact, That's what you see. Okay, 1 plus 8, 6 plus 5, the answer is 20. Let's take a look at this next example. Here, I'm going to show you the trick of balancing polyatomic units. Here we've got sulfuric acid, calcium hydroxide to produce water and calcium sulfate. Put an arrow right here. And you notice that you don't really you don't have any monoatomic chemical like oxygen here. But I would venture to say that I would start with my hydrogens in balancing this equation. So in terms of my hydrogens, I would say I have 2 here, and then I have 1 sulfate here. I've got 2 hydrogens here, and I've got 1 sulfate here. So the way I would do this is I would first take a look at my hydrogens. I can see that I got 2 plus 2, that's 4 hydrogens here. Okay, to get 4 hydrogens here, I would need to put a 2 right there. That would give me 4 hydrogens. My sulfate, I've got 1 sulfate here, and I've got 1 sulfate here. So by balancing my sulfate as a unit, I don't have to worry about the sulfur or the oxygen in the balance equation, because I see that I have 1 SO4 right here. So I've got 1 SO4. When the polyatomic unit stays intact, balance it as a unit, I've got 1 SO4 here as well. Okay, now let's take a look at the calcium. I've got 1 calcium here, 1 calcium here. So my calcium is okay. And if you look at the very last step, balance my oxygens. Don't worry about the oxygens here, because you've already taken care of those oxygens in here. What I have is 2 oxygens right here, because I got 2 hydroxide, I've got 2 oxygens right here. So I've got 2 oxygens. So that's a balance equation. What is the sum of the coefficient? The sum of the coefficient is 1 plus 1 plus 2 plus 1. That would be a total of 5. So the answer would be B, 5. So those are just examples of balancing chemical reactions. You should try these. Remember, these are combination reaction. Let me just do one real quick. You have 1 aluminum, 2 aluminum here, so you put a 2 right there. You've got 2 bromines here, you got 6 here, you put a 3 right there. That's a balance equation. The sum of the coefficient would be 3 plus 2 plus 1. That would be a total of 6. Okay, that's just an example. That's a combination reaction. These two produces 1. This right here is the decomposition reaction. 1 produces many. Let's take a look at this right here. We've got 1 mercury oxide, mercury and oxygen. So this is your arrow. There's 2 oxygens here, so we put a 2 right there. We put a 2 right there. And that's a balance equation. 2 mercury, 2 oxygens, 2 mercuries, 2 oxygens. There's a 1 right there. The sum of the coefficient is 2 plus 2 plus 1. So that's a total of 5. Okay? That's your decomposition reaction. Let's take a look at this. This is your single displacement reaction. Let's take a look at this one right here. Your copper replaces your silver. You get copper nitrate. But notice that your nitrate, there's 2 of them. And then your silver is exposed or free. So balance the polyatomic unit. There's 2 NO3. I need 2 right here. There's 1 copper. There's 1 copper. There's 2 silver. Put a 2 right there. The sum of the coefficient would be 1 plus 2 plus 1 plus 2. That's a total of 6. 1 plus 2 plus 1 plus 2, that's a total of 6. Okay? So, let's proceed. to the next slide. This is your double displacement. Take a look at this right here. Magnesium and sodium, they switch. Magnesium will replace sodium. Sodium will replace chloride. Make sure that the chemical formula is correct. Magnesium's +2, phosphate's -3, so it's Mg3PO42. Sodium's +1, chlorine's -1. We can go ahead and proceed with balancing the equation. I have 3 magnesium here. I would need 3 right here. I've got 1 phosphate here, but I've got 2 phosphates here. I would put 2 right there. You'll see that I've got 6 chlorides. Put a 6 right here. And now everything's balanced. 3 magnesium, 2 phosphates, 2 phosphates right here, 6 sodiums, and 6 chlorides. 6 chlorides right here. The sum of the coefficient would be 3 plus 2 is 5, plus 1 is 6, plus 6 is 12. That would be the correct sum of the coefficient. And you can practice with the others. These are examples of different reactions that shows that a reaction has occurred, gas formation. How do I know there's a gas formation? Right here. You see the phase. Gas formation is the driving force. Okay. Here, weak electrolyte. Weak electrolyte is nothing more than the formation of water. You can take it at that. And usually involves acid-base reaction. A weak electrolyte is another sign for acid-base chemistry that a reaction has taken place. Why do we call water a weak electrolyte? Well, that will be covered in acid-base chemistry. And then a precipitation reaction forms, or precipitate forms. How can you tell if precipitate forms? Look at that phase right there. That's a solid. That's a solid. It means that you start with aqueous solutions, but you get a solid forming. This right here, what would be the product in this reaction? It's a double displacement reaction. The hydrogens replaces the manganese. You get H2S. And the manganese replaces the sulfate. You get MnSO4. Remember that sulfate is -2. The manganese here is +2. So it's going to be +2 here as well. That would be the correct formula. That would be the correct formula. All we got to do is balance this equation. And the way you balance it is you got 2 hydrogens. You've got 1 sulfur, 1 manganese, 1 sulfur. It's already balanced. The sum of the coefficient would be 4. 1 plus 1 plus 1 plus 1. Here's another acid-base reaction. You can go ahead and practice balancing these. How do you know it's an acid-base? Because this, whenever you got a chemical and you have H in front of the formula, it tells you it's an acid. Whenever you have a chemical and you have OH, it tells you a base. Another type of base is ammonia, NH3. So these are acid-base. Acid-base generally forms water, neutralization reaction. And then these are your combustion reaction. Right here. Let's balance this last one here. We got 4 carbons. We want to put 4 right here. 10 hydrogens. We want to put 5 right here. Okay. We balance the oxygen last. If we take a look at this, this will give us 8. This will give us 5. 8 plus 5 is 13. So the question is, we've got 13 oxygen. How do I get 13 oxygens in this side? Fractions, 13 halves. Now we multiply the whole equation by 2. Why by 2? Because the denominator for that fraction is 2. So we want to multiply everything by 2. This now changes to 2. This now changes to 13. The next one changes to 8. And the last one changes to 10. So what is the sum of the coefficient? When you balance this and you don't leave an integer, 2 plus 13 is 15, plus 18, that happens to be 33. So the answer would be 33 in this particular case. So that's how you would balance chemical reactions. Remember that when you have a chemical reaction, the law of conservation of mass has to be obeyed. You got to remember that when you start a chemical reaction, you've got to make sure that you have the correct chemical formulas. You got to remember the hints that I told you. Save the monoatomic chemical for last. Start with your most complicated chemical. Use fractions to balance odd number of atoms. Balance polyatomic ions as a whole if it doesn't break up. And then remember the different types of reactions we covered. The combination, decomposition, single displacement, double displacement, and combustion.